Hello, everyone. We're working through statistical methods for rates and proportions, chapter 12, section 2, part 2. In this section, we're going over multiple Poisson regression. And the section starts off with the derivations of the multiple Poisson regression. And then we're going to move on to an example, which is given in table 12.2 on the nursing home data. The bed is the number of beds in home. The T days is the annual total patient days in hundreds. PC Rev is the annual total patient care revenue in millions of dollars. NSAL is annual nursing salaries in millions of dollars. FEXP is annual facilities expenditures in millions of dollars. And rural is 1 for rural, or 0 for non-rural. So I've saved this data into a file on my desktop. Another option you can use is the file.choose if you're not sure what your file extension is. And I'm going to read in that data and display the first 10 rows. So we have a unique identifier of unit, and then we have the bed, the total patient days, the annual total patient care, the nursing salaries, the facility expenditures, and rural. So I can do a summary of data just so that I can see what this looks like. And it looks like the average beds are 93.27 in a facility. All right, I'm gonna let Y be the beds, and the sum of Y will just give me the total number of beds across all the facilities, 4,850. Okay, so in this section, we're going to build a few different models. These models are written out on page 352. And the first model just has the PC Rev, right? The patient care revenue, the nursing salaries, and the annual facilities expenditures, right? So we just have PC Rev, nursing salaries, facility expenditures. We're going to offset the log total days in our model. Okay, for model 2, I'm going to just skip down. We're going to still have the patient days, the patient care revenue, the nursing salaries, the facility expenditures, but now we're going to add an interaction term for the patient care revenue with the nursing salaries, the patient care revenue with the facility expenditures, and the nursing salaries with the facility expenditures. In model 3, we're going to have all of those things, plus we're going to have whether or not the facility was in a rural area or not, okay? And in model 4, this is going to be a saturated model where we give 1 coefficient per observation. Okay, so going to model 1, we're going to run this Poisson regression model. And let me make sure that I highlighted everything. There we go. Okay, so fit1 was our GLM model, and then s.fit.1 is the summary of fit1. So what do we notice? We notice that we get the coefficients of the model, the standard errors, the z values, and the t. Okay, so this is telling you whether or not those main effects are significant or not individually. And you can notice that you can find your residual deviance here in the output, right? We could also obtain the inverse information matrix for our coefficients by doing s.fit.1 $ covariance unscaled. And then that will give us our variance covariance matrix between all of our coefficients here. Now our mu hat i's, these are our fitted values. And in order to obtain the log likelihood, we are going to use equation, it's right under 12.18, right? Which gives us our equation for the log likelihood of our estimated coefficient. So this is the log likelihood for model 1. And we get the value that was shown in table 12.3 in our textbook on page 354. We get the value of 17,446.37. Now our values might be slightly different than the book because of rounding, or maybe I possibly typed in one of the values incorrectly when I was inputting table 12.2. All right, if the model is true, right, then we can say, right, we expect that our residual deviance should be distributed as a chi-squared random variable with degrees of freedom equal to the model's degrees of freedom. Okay. Residual degrees of freedom. So what we're going to do is we're going to use the p chi-square function in R. We're going to tell it to pull off the deviance, right, of the model. And then we're going to use the degrees of freedom as the residual degrees of freedom. And you could either do 1 minus p chi-square in this way, or you could do p chi-square fit.1 $sign deviance degrees of freedom equals fit.1 $sign degrees of freedom dot residual, and you could just say lower dot tail equals false. That's another option for coding this, right? And we get a value that is very, very close to 0. It's very, very small. So we know that we have a model here that these variables are significant in predicting the outcome variable of the number of beds. Okay, so in our second model, remember, we're going to fit the model with interaction terms, and we're going to run through the same thing. So we're going to make sure that we can get the summary of our model fit. We're going to calculate our log likelihood for our model 2. Okay. And we're going to verify that's the correct number found in table 12.3. We should get a log likelihood of 17,461. That's looking good so far. Our summary gives us the summary of the maximum likelihood estimates and the standard errors of the Poisson regression model. Okay, so here we're getting all of these individual beta hats. We're getting their associated standard errors, the z value and the p values. So this is saying, is the interaction term between total patient care revenue and annual nursing salary significant? And we find that it is. All right, we can get the inverse information matrix by pulling off the covariance dot unscaled. And what we might like to ask more than just, are these particular terms significant? We might use a partial F test to say, are all these additional interaction terms adding predictive value to the number of beds, right? Given that we already have a model with patient care revenue, nursing salaries, and facilities expenditures already in the model, right? That's the definition of our partial F test. And we could do this by saying ANOVA of fit 1 and fit 2. And that gives us our test statistic of 29.38. And you can follow all of this in the book on page 355, right? We can just use the ANOVA and get that, or alternatively, we could have done the difference of the log likelihoods that we already found and multiply by 2. Either way, that's going to be 29.38. We have 3 degrees of freedom, right? And so our p-value is very, very small, which means that the interaction terms are jointly significant, meaning that they add predictive value compared to a model where we just have the main effects in the model. Okay, another thing that we could have done is we could have used the walled statistic for these three coefficients. And what we could do is we could just pick off the coefficients for the interaction terms, right? And we could just pick off the block associated with those interaction terms, which is what I'm doing here by just choosing the 5 through 7th row and the 5 through 7th column. And then what I'm using is the W squared that's given on page 355, about halfway down above table 12.4. And I am calculating that W squared using R. And we get the same value here as they did in the book, 29.33. Okay, so oh, excuse me. In the book, it's slightly different, but I think that this is because that they're rounding before putting everything in, and I did not round the values, so these numbers are slightly different. Okay. So what we can do here is we could put together all this information that we just got, right? Which is, we can say, what was the actual deviance that we saw in fit 2, right? What was the fit 2 degrees of freedom? The fit 2 deviance divided by the degrees of freedom for the residuals, right? That's our chi-squared value. And then we could add on the p-value. So essentially here, and I'm going to add on one more thing, which is the log likelihood of model 2. So if I take all of these pieces here, then I'm essentially getting the second row of table 12.3, right? So our log likelihood is 17,461. The deviance was 215. The degrees of freedom, n minus p, was 45. The chi-squared value that we found was 4.79. In the book, it's 5.23. Once again, I think this is slightly different due to rounding, and the p-value is very small. The p-value is approximately equal to 0 in this case. All right, moving on. We're going to go to model 3, where we include rule in the model in addition to all these other pieces. So we've already found that this interaction terms are significant compared to the rest. Now we want to find out if we should add rule into the model. And so we can do our summary of our coefficients, right? And since there's only a difference of one variable, this test will really be equivalent to just testing that single variable being significant, but you can carry it out as extra practice. We can get our mu hat i's for this model, and that will lead us to get our log likelihood, 17,467. And we can find out what is our variance covariance matrix for this model. So we have all of our terms and the interaction terms in one model. And from there, we can continue on to do all the separate pieces, and I'll let you do that as an exercise. Okay, so you can verify table 12.5 with your s.fit.3. These values should be very, very close to what you find in table 12.5 on page 356. All right. Last thing, we can fit a saturated model, and essentially what we're doing here is we are fitting the model where we're going to give one coefficient to every single observation in the model. So since the unit just defined the unique observations, I'm just treating the unit as a factor and then fitting a model. So here, notice that there's a coefficient for every single bed here. All right. And what we can do is we can get our fitted values for that model. And that way we can get our log likelihood for our saturated model. And when we do that, we get the value of 17,568.91. So essentially that has finished off table 12.3 for you. So just so everyone knows, you can continue to work on Poisson regression. We're not going to cover section 12.3, but if you have questions about it or would like to know more, please feel free to read it and ask questions the next time I see you. All right, have a good day.